Nick here, M0NTV, and welcome back to my shack and to another video. Now, one of the most watched videos on my channel by a country mile is one that I made last year on designing a simple transistor amplifier, and it's still getting hundreds of views even today, which says to me that's something that a lot of people are interested in. And one of the questions that came to me after that video, and that video, if you've not watched that video and the one after it, which is about small signal analysis, that's how you calculate the AC parameters and things like the input impedance and the output impedance. And the first video was about how you calculate all the DC biasing and the voltage points and the currents in your circuit. If you've not watched those two, I would suggest you go and watch those first. They are a bit long, but I'm going to be building on that information in this video and the one that comes after it. One of the questions that came was, can we use that technique that you've just told us about and that basic design of a common emitter amplifier for radio frequencies? To which, of course, the answer is yes, but there are things that we need to consider and take account of when we're building for radio frequencies that we don't when we're building for audio frequencies. And working at these much higher frequencies means that there are things that come into play that we just didn't have to consider last time because I was building an audio amplifier. So I kind of thought, actually, this is interesting, because, and this may be an interesting subject for people that want to go on actually and build and design their own small signal RF amplifiers. So that's what we're going to be digging into this time and next time. And really, I want to look at the challenges, and there are a number of challenges here. I mean, there's the challenge of impedance matching. Now, audio frequencies, we're not really bothered about impedance matching. In fact, all we really need to make sure is that the input impedance of our stage is at least 10 times higher than the output impedance of the previous stage, so we can maintain the voltage levels. Now at RF, we're not really that bothered about voltage levels. It's more about preserving the power gains that we make throughout the radio. And the way that we do that, of course, is because maximum power is transferred when impedances are matched, and that's why we match impedances. And I've done many videos on impedances and matching them with LC networks, and I've done a couple recently on broadband transformers, so you can check all those out if you're interested. But there's two other particular things that may not be obvious, particularly if you're just dipping your toes in the water of this RF design stuff. And so I think it was worth doing a couple of videos on these. So that's what I'm going to do. So this one I'm calling the bugbear of beta. And beta, or HFE as it's known on the data sheets, is the current gain of your individual transistor. That's what we're going to look at this time, and the next video I'm going to call the curse of capacitance and looking at capacitance that we didn't want and didn't ask for, but nevertheless we have to deal with when we're working at RF frequencies. So as always, thank you for watching. I hope that you find something useful here to help you in your own designing and building. And as always, I hope you enjoy. So let's get started. The challenge of designing a simple small signal transistor amplifier, but for RF. And that is the one that I built, which you'll see more of in a bit. Now, this was the original design of the common emitter stage, the first stage in that audio amplifier that I built in the video that I mentioned before. Now, obviously, if we were to use a similar thing for RF, then we're going to have to do something about these capacitors, because these capacitors are large. 100 microfarads, and that's because it's an audio amplifier, so they need to pass those low frequency audio signals, and to do that you need to have large values of capacitors. These, the green biasing resistors, really don't need to change very much. You'll see in the next slide that they change a little because I've played around with something, but you basically could swap these to something more sensible, keep these as they are, and jobs are good 'un as far as DC biasing of your amplifier is concerned. So let's have a little look. So this is what I actually built, and you'll see I swapped all the caps out for caps that are an order of magnitude lower. So instead of 100 microfarads, these are 100 nanofarads, which will pass those higher frequency RF signals that we are dealing with. There's very little change to the collector resistor. Incidentally, I'm not going to go through the whole methodology of how I worked all these values out. You'll have to go back and watch that video because I go into a lot more detail there, so I'm not going to repeat myself. But that's pretty much the same. It's just basically making this point on the collector midway in terms of the voltage that we've got to play with. So we've got the maximum scope for the signal with its positive and its negative excursions of the sine wave. This is very similar. This is setting the current. So I've got 10 milliamps basically going through the collector circuit. Notice we are fully bypassing this emitter resistor, which will increase the gain but won't upset the DC biasing. The only real change is in the voltage divider biasing. I just made these values a little lower than they were in the previous one, just because I wanted a little bit more current going through the voltage divider. The rule of thumb is that you need at least 10 times the amount of current going through here as you have going into the base. But that's really a minimum. So I erred on the side of caution, and I think I went for about a milliamp. So I've got 10 milliamps going through here. I've got 1 milliamp going through there. I wanted to make it as bulletproof as possible to any changes in the DC beta of individual transistors. And I say that advisedly because that's the point of this. It's because different transistors have different values of DC beta, and you don't want to plug a different one in and get completely different results. So this basically makes sure that any variations because of the DC beta, which cause the current to rise and fall more or less, will pale into insignificant compared to the current that we've got flowing through here, so it won't upset the DC biasing. Now, it doesn't bulletproof you from anything else to do with beta, but more of that in a moment. Now, when I designed my simple transistor amplifier, which was an audio amplifier, I was able to make one important assumption. And that assumption was that the gain of the transistor, the beta, the HFE as it's called in the data sheets, the gain of the transistor would be the same for my audio signal as it was for my DC bias. Let me say that again. I assumed that the gain for my audio signal through this transistor, this 2N3904, would be the same as it was for my DC bias. And I was quite justified in making that assumption. However, when it comes to using this same transistor, this 2N3904, at radio frequencies, we can't make that assumption anymore. Let me show you exactly what I mean and why. So here is my simple RF common emitter amplifier. Note and this is obviously an LT Spice simulation. Note I've disconnected the signal source. So we've only got the DC bias going through this here. And what we want to do is we want to measure what is the beta of this transistor, at least this LT Spice model of the transistor. And of course, the way to do that is to calculate beta. And we know that beta is actually the current at the collector divided by the current at the base. So let's do that here. So if I put the current in the collector, yes, these oversized cursors are great for people watching, but not so easy to do. So it's ICQ1, and we're going to divide that by IB brackets Q1, and press OK, and there we go. So that is 307.5. So that is the DC beta. That's the DC current gain of this model of this 2N3904. Okay, what I'm going to do now is I'm going to swap this around, and we're going to swap from doing the transient analysis to doing an AC sweep. So now I've swapped over from the transient analysis to an AC sweep. And if you look here at the graph, you'll see on the x-axis down the bottom, we're sweeping from 100 hertz up to 100 kilohertz. And up the y-axis again, we have the beta. And you'll notice for that entire sweep, it's pretty flat, you know, and it's hovering somewhere around 290, which, you know, is not a million miles away from the 307 that we just got at DC level. So you can see why, if you're going to use this 2N3904 in an audio amplifier, it's absolutely fine to assume that the current gain that your audio signal is seeing as it works its way through the transistor is pretty much the same as the DC bias is seeing. So we can use this same value of beta. But what I'm going to do now, and I'm going to keep all the scale along here the same, but what I'm going to do is I'm going to enlarge the sweep. So we're going to start at 100 hertz, but instead of finishing at 100 kilohertz, we're going to finish at 100 megahertz. Okay? And just look what happens to beta when I do that. Wow. Take a look at that. Talk about falling off a cliff. I mean, you know, we're getting up to, what are we here? 132 kilohertz. And then once we get to about, somewhere near 250, 260 kilohertz, it's downhill all the way. So even at 1 megahertz, around about 1 megahertz, beta's down to 153 from, 290. But at our frequency of interest, we've got to come right the way down here and try and get roughly onto 7. There we are. 7.024 megahertz. 29. That is one heck of a difference from 290. Right, factor of 10 difference. So that is quite incredible. Now, when it comes to biasing this thing for DC, I mean, DC is DC, right? So it won't make any difference. We can use that 300 and whatever it is, and that'll be fine. But when it comes to analysing how our RF signal is being amplified, we realise that the frequency makes all the difference. And what's also really difficult, as you can see here, I mean, if you were building an audio amplifier for all the audio range, it's pretty flat. But if you were trying to do a kind of wideband RF amplifier with this thing, you know, the gain is going to vary so much depending on the frequency that you're going to try and put through it. That's going to be a challenge. So it won't be remotely flat at all. Now, what on earth can you do about this? Does it mean we can't use a 2N3904? No, it doesn't mean we can't use it, but you do need to be aware of this. And so when you're calculating how much gain you're going to get out of this thing, you'll realize it's a lot less than if you were using it at audio frequencies. And that's because this transistor is a general purpose transistor. It's not even designed to be used at some of these frequencies we're trying to press it into use at. Let me just show you what happens now if we swap this transistor out. And I'm going to keep all the rest of the biasing the same. I'm just going to swap this transistor out and put in a couple of different transistors and keep all this the same and just see what that does to the beta of our circuit. So all I've done is just duplicated this original design 3 more times, but I've swapped out the transistor for 3 other popular transistors. I've kept everything else the same and plotted those traces on the same chart here, and I've labelled the traces here so they're easier to see what is what. So here's the original one that we've just looked at, the 2N3904. The second one, the blue one, I tried a 2N2222, and you'll see there's less gain in this device, but it doesn't really perform any better, in fact worse than the 2N3904 for the RF frequencies we're interested in. And then we drop down to these last 2. So now the gain has really gone down here, but look how straight this is. This is the BF199, and that has a much higher transition frequency, as we call it. So it's going to have a much better beta for higher frequencies, and indeed it does, and that performs a lot better. So it still drops off, but we've still got more gain by the time we get down to our frequency of interest. So, you know, what do we get in here? About 44 or something. But check out this bad boy in blue, the MPSH10. Now, I first came across this when I was pretty new to homebrewing, actually, in Eamon Skelton and Elaine Richards' classic book, Building a Transceiver. And actually, the book even falls open on page 16, where I've built this one circuit that he designed so often, which uses 2 of these in an IF amplifier that he designed, or a post-mixer amplifier. And you can see why he uses them. Now, yes, there's a lot less gain, but look how flat that is right into the lower HF regions. So when we get to 7 megahertz here, if I can find it, we're 64. Well, that's a lot better than the 27 that we were getting down here. And I think this just underscores the point that if you want to maintain the gain in your RF amplifier, then really you need to use a transistor which actually is built to handle those frequencies. And whilst you can, of course, use any transistor you want, and of course you can use these, but you're going to have to accept some shortfalls, and pretty steep shortfalls if you're going to do this. And actually, this will be compounded in the next video when we talk about another of the challenges. Effectively, by using the 2N3904, we're using something that it wasn't designed to be doing. Now, that's not to say we shouldn't do it. It's of course possible, but that adds a layer of complexity if we are to design it and to build it correctly. So it's a bit of a trade-off. Yes, you can buy something that's cheaper and plug it in, but it's not going to work as well as something that was designed to be used at that frequency, and it means you have to do more work if you want it to perform in the way that you want it to perform. Well, big deal, you might say. Who cares if we have to settle for a bit less gain at RF frequencies? But that's not the kicker. The real issue is what I just referred to, which is the fact that that slope of in the RF bit that we're interested in the HF portion, is so steep, which means that the frequency on the x-axis, for a tiny increase in frequency, there's a large decrease in beta. So it's highly frequency sensitive. And why that is so unfortunate for our point of view is that it's this value of beta, not the DC, this value of beta, which is used to determine the input impedance of the amplifier. And let me show you how that works. Now, I'm not going to go into all the calculations of small signal analysis. You'll have to watch that video that I made previously if you're interested in that. But I am just going to step you through why the value of beta is so critical when it comes to calculating our input impedance of the amplifier. So the input impedance is usually seen as two different resistances in parallel with one another, and they are what we call RB and R pi. Well, RB is just itself a parallel combination of resistances of R1 and R2. So that this is the voltage divider, and it's because at AC level all the capacitors are seen as short circuits. The DC power supply is just seen as a ground, and that means that actually this is AC grounded, that R1 is actually in parallel with R2. We could draw R1 down here next to R2. So these two effectively are seen as in parallel with one another. And so if we do that, that gives us a parallel resistance of 1.45 kiloohms. And that is in parallel itself with R pi. Now R pi is the small signal input resistance of the transistor seen looking into the base. And the way that that is calculated, it first of all looks at the base emitter junction and sees a tiny resistance. It's known as R sub E, or little re, which is this intrinsic resistance of this diode drop, basically, the base emitter junction. And it's calculated, it's the thermal voltage, which is 25 or 26 millivolts divided by the collector current, which in my case is 10 milliamps. So that gives you 2.5. And so you've got this tiny amount, 2.5 ohms, but that's going to be multiplied by beta plus 1, which is the current gain of the amplifier, and the plus 1 is the actual base current itself, because if we were looking at the collector we would see beta, but if we're looking at the emitter we see beta plus 1, because the current flows from the base to the emitter. So we can see already now beta is going to play a key role here, because if we're going to parallel this with this, and we know this is 1.45k, and this that we're multiplying beta plus 1 by is only 2.5 ohms, you know, this is going to have a key role in determining the input impedance, and so it actually is. So at 1 megahertz, this is not completely accurate. All I did is I just looked at those traces that I showed you a moment ago and roughly said at 1 megahertz it's roughly, according to LT Spice, beta was about 153. So don't take this too literally, but it just gives you the idea. So let's say that's true. So 153 plus 1 multiplied by 2.5. But at 7 megahertz, as we saw, beta was more like 29. And that's going to be have 1 added to it and multiplied by 2.5. So what that means is that R pi, the small signal input resistance of the transistor seen looking into the base, at 1 megahertz would be 385, but at 7 megahertz would only be 75. So that's a big difference, and that is going to play out now in the calculations of input impedance. So if we plug these numbers in then to our original formula, that would give us at 1 megahertz an input impedance of 304 ohms. And if we plug the numbers in for 7 megahertz, that would give us an input impedance of just 71. So now, if you were just building this amplifier for a spot frequency, say an IF frequency, where you haven't got a broad swathe of frequency that you're interested in, then that would be all right. And at 7 megahertz, I mean, 71 ohms would be great. You wouldn't really need to do much impedance matching at all on the input. But the problem is, if you want to do anything more broadband, then how on earth are you going to match impedances? Because you could build some kind of matching network for 304 ohms, but then it's going to be hopelessly out of kilter when you get to 7 megahertz. So, you know, it's really tricky. And the problem is, of course, because it's not flat. You know, beta is in free fall with a 2N3904 by the time we get to these frequencies. And that is why it's such a difficult challenge. Now, you can calculate beta by hand, and this again is very rough and ready. There is another formula. I'm not even going to trouble you with it here now because time's getting on. But there is a kind of shorthand thing, and many thanks to Charlie Morris, ZL2CTM, who was the first person who highlighted this to me, which is to take the transition frequency, the FT, which you find in the data sheet, and divide that by your frequency of interest. Now, the transition frequency for a 2N3904 is usually quoted as 300. And you might be tempted to think, well, you know, what's the problem? I mean, 300, we're trying to use it at 7 megahertz. I mean, that's well within spec. But you need to remember what the transition frequency actually is. This is the frequency at which the current gain of the transistor falls to 1, to unity. In other words, by 300 megahertz, it's not amplifying anything at all. So it's tricky. But if you do the sums here by hand, you get 300 divided by 7 would give you a beta of 42.8, which is higher, of course, than the LT Spice version. And at 1 megahertz is much higher. 300 divided by 1, 300, well, yeah. What you also need to remember with all of this is LT Spice is clever. And the small signal model that LT Spice uses draws in not just these fag packet calculations that I'm talking about here, but a lot of other things as well, some of which we will mention in the next video. All I'm saying is there's more going on, and it is frustrating because I've designed it on paper, work it all out, model it in LT Spice, and you think, well, it looks like a different amplifier, you know, none of the figures seem to match. And that's because I'm using a small signal model and trying to do some of these calculations by hand. LT Spice is doing the same thing, but better, basically, and with access to a lot of other things. And yes, I could learn to do all these things, but at the end of the day, you have to think, well, it's probably quicker, easier, and more accurate to use LT Spice. But because I like trying to understand how things work, you know, I make an effort. But just be aware that's why some of these numbers will be different. I think it's just worth pointing out one last thing, which is you can't have your cake and eat it, a wonderful English expression to say that you have to accept some compromises. You can't have it all your own way, Because the truth is, when it comes to designing a small signal transistor RF amplifier, there are three main factors which have to be considered. And these three competing factors are dynamically related to one another. And really anything you design is going to be a compromise between these three. And you just can't have it all. Because if you optimize one, it will be at the cost of another. Let me show you what I mean. So the three things I would suggest are complexity, expense, and performance. So basically we want it to be as simple as we can get it. We want it to be as cheap as we can get it. A lot of us are radio hams, we're tightwads, we never want to spend any money on anything. But also we want it to perform well. And I'm afraid you can't tick every box to the extent that you would like. Let me show you what I mean. And we're going to read across these here. So if you want a circuit that's simple and you want it to use cheaply, easily available parts, you're going to have to accept some compromise performance. You can build it simple, you can build it cheap, but it's never going to work quite as well as you hoped. And this is what we've seen exactly with using this 2N3904 at frequencies that it's not really designed to operate on. Yes, we can get it to work, and I've built one and it works, but not as well, you know, and there's problems with matching the impedance and with the gain flatness. But you could say, all right, okay, well, we still want it to be cheap, but we want it to work better. Well, fair enough. And you can do that, but that means increased complexity. And what that means is that as it stands, that amplifier that I built is not going to cut it for what I'd like to use it for, which means I've got to add some additional circuitry to try and overcome the limitations. So yes, we can keep it cheap. Yes, we can get it working better, but it's going to mean more complexity. Thirdly and finally, if you say, well, hang on, I want it to work well, I want an optimized performance, and I want it to be simple. Well, you can do both of those things, but it's going to cost you more, right? And that means replacing the transistor with one that's actually designed to operate at RF. The MP-SH10s are not ridiculously expensive, but they are more expensive than the 2N3904s. So that is the conundrum that we're faced with. You can't have it all. And really, you have to decide what you want to go for, you know? So can you accept less performance? Can you accept increased complexity? Or are you prepared to spend a bit more? And really, that's only something that you can decide for yourself. So I designed it on paper. I modelled it in LT-Spice, and yes, I built it in reality. And next time we'll actually do a bit of real world testing of this amplifier, and hopefully you'll be able to see some of the stuff I've been talking about. But as it stands at the moment, well, it's fallen foul of the bugbear of beta. But unfortunately, it gets worse, because it's also got to contend with the curse of capacitance, and that is coming next time. As always, I need to say to you, I am no expert in any of these things. It's just a hobby. I enjoy learning and sharing some of this stuff in the hope that it's going to help somebody else. So I do hope that you have found something of interest here, something that's going to help you in your own designing and building of electronic stuff. If you have enjoyed it, please remember to like and subscribe, and then you can keep up to date with all my home brewing adventures. But thank you very much for watching. Until next time, look after yourselves. 73. Bye-bye.